All right, hi everyone. Welcome back to the section 4.4 video. And in this video, we're going to solve another non-homogeneous differential equation using the method of undetermined coefficients. But within this method, we're going to uncover a glitch that occurs within this method. And we're going to learn how to deal with this glitch and be able to still solve the differential equation despite the glitch. Okay, so this is a new error coming up within the method, and we're going to learn how to deal with it. So let's go about it normally. Let's identify that this y double prime minus 2y prime plus y is our homogeneous component. And with our homogeneous component, we would get our complementary solution. And that e to the x is our non-homogeneous component, and that's where we get our particular solution from. And just remember that the general solution that we're trying to obtain is the complementary plus the particular. Okay, so always the first thing to do is solve the complementary solution, the homogeneous part. So let's go ahead and get going on this portion. So here I'll say solution. And so step one is to solve the complementary solution. So step one, solve the complementary solution using the auxiliary equation. And that's from section 4.3. Okay, so the homogeneous component, we'll say HOM, is that y double prime minus 2y prime plus y, and homogeneous is it would equal 0. Okay, so remember our auxiliary equation that we're trying to solve for this constant coefficient homogeneous differential equation. The standard form for these constant coefficients would be a double prime plus by prime plus cy equals 0. And so our coefficients are 1, b equals -2, and c equals 1. And so this creates the characteristic equation m squared minus 2m plus 1 equals 0. And so this is factorable. It factors into m minus 1 times m minus 1. And so we get roots m equals 1 and m equals 1, but this is a repeated root. Okay, and when we have repeated roots for a constant coefficient homogeneous differential equation, recall that the solution is, y equals c1 e to the m1x plus c2 x e to the m1x. Okay, so just remember that's the solution when we have a repeated root. So our complementary solution would be y sub c equals c1 e to the 1x, so that's just x, plus c2 x e to the x. Okay, so that's our complementary solution. Okay, so we got our complementary, wasn't too bad. Let's go ahead and jump now to our particular solution. So we're going to need to form a trial particular solution. So the non-homogeneous part of this differential equation is that e to the x. So we're going to use this e to the x to form our trial particular solution. And this is pretty straightforward because our particular solution is just a constant a attached to the e to the x. And this is good news because this just means we only have to solve for one constant coefficient a. Instead of like a, b, c, d, we just have a to figure out. So that means it could be less work for us. And so we have a, and what we need to do now is get its derivatives to plug back in. So yp prime is just going to be ae to the x. And then second derivative is also itself. Okay, so let me move this over. I like to write trial. But okay, so that is our trial particular solution and its derivatives. So what we're going to do now is step 3. Plug in the particular and its derivatives first and second into the differential equation and solve for just a. Okay, so our differential equation, what is it again? It's y double prime minus 2y prime plus y equals e to the x. Okay, so we're going to plug in our particular solution and its derivative. So this becomes a e to the x minus 2 a e to the x plus a e to the x equals e to the x. Okay, so this ends up being a e to the x minus 2a e to the x plus a e to the x equals e to the x. Well, what happens here? These all cancel out with each other. And so what I'm left with is 0 equals e to the x. Well, that doesn't make sense. That doesn't make sense at all. I'm not solving for a, and e to the x never equals 0. So we have two weird situations going on right now. So this right here is no solution. This is not a solution. I didn't figure out what a is. 0 doesn't equal e to the x. So this means that my particular solution fails us. But we've done everything right. We picked the right particular. We plugged them derivatives in correctly. What's the issue here? Why does this fail? Okay, why does my particular solution fail? Well, that's because a e to the x, my particular solution, is already present in our complementary solution. We have c1 e to the x. That's already present in my particular solution, in my complementary solution. It's already here, already a constant times e to the x. So if I'm going to have two of the same functions, well, that creates linearly dependent solutions. Okay, so this creates linearly dependent solutions. And we cannot have linearly dependent solutions in our general solution. We need linearly independent solutions. So, which we cannot have in a general solution. Let me move this over here. I have more room over here. Okay. So what would I do? One thing we could do to deal with this issue is tack on an X to the particular solution. So let's see. We could say, so we could say, so how about the particular solution ax e to the x? Would that work? No, that wouldn't work as well because x e to the x is also present in our complementary solution because we have C2x e to the x, which is up here in our complementary solution. So what can I do now? Well, what I could do is just tack on another x. So I would have x squared in my particular solution. So let's do this. Step two. Let's go back to step two. And this is step two, redo. Okay. And what does step two do? It's forming a trial particular solution. So my particular solution now, as we notice, we have a glitch, would be ax squared e to the x. And there's no x squared e to the x in my complementary solution, so we know this would work. Okay, so let's go ahead and get our derivative. So derivative of a particular solution, this is going to require a product rule. Okay, f g prime plus g f prime. F here would be ax squared, g would be e to the x, f prime would be 2ax, g prime would be e to the x. So this would be ax squared e to the x plus 2ax e to the x. And I need a second derivative. And so this is going to require essentially two product rules. One of them would be exactly the same in that it would be ax squared e to the x plus 2ax e to the x. Okay, but we're going to need a different product rule. So dealing with 2ax e to the x. So, we could say f equals 2ax, g equals e to the x, f prime is 2a, g prime is e to the x. So this turns into, the derivative turns into 2ax e to the x plus 2a e to the x. Okay. And, it's coming from this derivative. And let's see, I think I could combine some like terms here. We have 2ax e to the x. twice, so that could become ax squared e to the x, and now becomes 4ax e to the x plus 2a e to the x. Okay, so step 3, again, redo. We're going to plug in the particular and its first and second derivatives into the differential equation. And really, we're only solving for a. So that's what's nice about this. But let's go ahead and plug our particular and its derivatives in. So our differential equation, let's just write it again for the sake of it. Y double prime minus 2y prime plus y equals e to the x. Let's plug in our values or our equations. So this would be a x squared e to the x plus 4ax e to the x plus 2a e to the x minus 2 times ax squared e to the x plus 2ax e to the x, and then plus ax squared e to the x, and that all equals e to the x. Okay, so what we need to do now is distribute in that -2 and then drop the parentheses, and we're going to see some nice algebraic simplification here. So if we distribute in the 2, drop the parentheses, what we get is ax squared e to the x plus 4ax e to the x plus 2a e to the x minus 2ax squared e to the x minus 4ax e to the x plus ax squared e to the x equals e to the x. Okay, so if you can see some of the like terms, we have a ax squared, negative 2ax squared, and a ax squared. Well, these all cancel out. The x squared terms cancel out. And the 4x ax e to the x cancels out with the negative 4ax e to the x. So really all I'm left with is just 2a e to the x equals e to the x. You know, we can equate the coefficients like we typically do. And so this is just 2a equals 1 because there's like a invisible 1 right there next to the e to the x. And so really a is just 1/2. And that's pretty much it for our coefficients. We only have a to figure out, so that works out very nicely for us. So we got a, all right? We need to plug a into our particular solution. And what was our particular solution? It was ax squared e to the x. And so our particular solution is just 1/2 x squared e to the x. Okay, step 5 is now our general solution. Step 5, general solution. Remember, general solution, as we wrote previously, is the complement plus the particular. And so what was our complement again? Our complement was C1 e to the x plus c2 x e to the x. And so our general solution would be c1 e to the x plus c2 x e to the x plus 1/2 x squared e to the x. And if you want to clean it up a bit, you can factor out an e to the x. So we get e to the x times c1 plus c2x plus 1/2 x squared. Okay, and that is our general solution. So just to backtrack a bit, we had a glitch in the method. This is our glitch. And when you have a glitch, that means your particular solution is failing. Okay, so you always want to keep an eye out, make sure you don't have any repeating terms, meaning linearly dependent terms in your solutions. And then it's just tacking on an x to your particular solution. Okay, so keep a track with that, recognize a glitch, and then, do your step 2 and 3 all together. But that's it for this video and the glitch in the method introduction. Thank you for watching, and I'll see you in the next one. Okay, take care.